My research deals with the modeling and simulation of integrated energy infrastructures. This means the connection of natural gas, hydrogen, electricity and heat infrastructures. The main software packages I'm working with, which are both available as open source, are pandapipes and DAVE. Today I would like to show you what possibilities these two software packages offer for the simulation of energy infrastructures in the context of hydrogen networks. In my research, I see the hydrogen infrastructure as part of the integrated energy system, as shown here in our paper. At the top, you see the sources of the energy system, and down here are the consumers. The hydrogen infrastructure, shown in the middle in blue, is connected to the electricity grid, here in yellow, via grid expansion and electrolysis. On the other hand, it is connected to the gas grid, here shown in red, via the concept of reusing the pipelines and infrastructures for a future hydrogen network. Modeling such complex system requires a lot of data that can be used in powerful and efficient simulation softwares. This idea in mind, I started to develop two tools, DAVE and pandapipes. DAVE is about creating synthetic grids based on available open data. The idea is to combine data and create electricity, gas and heating networks for every region in Germany and perhaps also the rest of the world. It is important to make the data available for easy use by people. Pandapipes is the Python-based fluid network simulator. It is programmed for water, heating networks, but also for natural gas and hydrogen networks. If you only change the fluid, you can theoretically also model CO2 networks or ammonia networks. But this is not implemented yet. So let's first take a look at the DAVE tool. Here's a short movie to illustrate the graphical user interface we developed. First, you need to select a region that interests you. This can be done by a postal code, by a town name, federal state names, also a NUTS region, like here for Swiss, but you can also upload your own shapefile or just draw the region you're interested in. Then, depending on the grid you want, you can select your voltage level, or if you want a natural gas grid model, then you can choose your pressure level. After pressing the Run DAVE button, DAVE is going to do its work. It's collecting data just for the region you selected, and in a few seconds it's providing you with the results. Here down on the page you will see on the left side a map with the resulting network, and on the right side there will be result tables. There it is. The blue buttons here are the junctions, which you can just get rid of to see the resulting pipes of the grid. In the future, or right now, on the version of the graphical user interface, you would be able to see the resulting tables on the right side next to the map. But the most important thing is now that you can download the data. And this can be done in data formats for your network simulation tool or your model. So right now we have implemented pandapipes models, pandapower models, but also for the gas grids, data models for MINS and for the gas lab. Pandapipes is an open source package which can be installed using pip in Python. It is a fluid system modeling tool. You can build pipe grids easily and calculate real networks with the so-called pipe flow. The method is based on the Kirchhoff laws, which are solved using a Newton-Raphson solver. You can learn more on pandapipes on the webpage on www.pandapipes.org or watch one of my other videos. Pandapipes is the little sister of PandaPower, a power grid software which was developed more than 10 years ago. We made sure that the data formats are very similar, so if you know how to use one software, you already have an idea on the other. You can learn more on PandaPower on www.pandapower.org. And the best thing is that you can both use together. If you look for the multinet package, it comes with the pandapipes distribution. You can learn more about this in my other videos. Now let's look into two use cases. The first here is dealing with the transportation network. There are some research questions which needed to be answered in the context of transportation infrastructure. Let's look at the question on the topology of the future hydrogen network, including the question of repurposing the natural gas network. You can see here in the picture in the green shaded region all the components which need to be taken into account for such an analysis. Here you can see the procedure how to do such a calculation, which we have also shown in our paper. We need data for scenarios and for the network topology. They are input for the network simulation. And the results are then documented, analyzed and interpreted here in the last step of the procedure. So the network topology could be taken from DAVE. Here on the right side you can see the DAVE data for a gas network taken from the Sigrid gas dataset. The dataset is then converted to network simulation tools. For example, it could be translated or transformed to pandapipes. Pandapipes can then be used to do a network simulation. This is basically what we did in the TransHydSys project. For the project, we generated a special project graphical user interface with two main functionalities. First, you can download what we call source data, so data which come directly and unchanged from different sources. Here, for example, the information on the federal states. In DAVE, you can see the data then on the map on the right side, but also the table with the informations on the left side. Then you can download the data. The second function is the download of generated data, like the gas grid data from the DIW Berlin Department of Energy and Resource Management, called now TUBA data. Here you can choose the network, the scenario, and then visualize the data again on a map on the right side and in a table on the left side. After that, you can download the data again in three different formats: the original DAVE format, the pandapipes format, and the MINS format. With this information, you can then search the perfect topology for a given hydrogen demand and do a hydrodynamic calculation of the network, resulting in flow capacity, flow velocity, and pressure values. The second use case is dealing with distribution networks. The questions of future hydrogen distribution networks are about possible fuel switches, but mainly for the industry and mobility, but also on the future of efficient heating solutions in the residential sector. One important decision for each house owner, which is still connected to a natural gas network, is about its future heating solution. Should it be based on electricity, including a heat pump, on biomethane, or maybe on hydrogen? Depending on his choice, we need to plan the network transformation. Maybe it is expansion of power grids because of the new heat pumps, or a new infrastructure for the production of biomethane. Or maybe it's a repurposing of the natural gas network towards a hydrogen network. For such studies, we need, again, a lot of data. But real data are not always available. So Dave can create synthetic, artificial, non-real grid infrastructures by using OSM data and a lot of expert guessing, in particular when it comes to detailed network assets. But nevertheless, we can get power grids and gas grids out of this tool. Using these data, regional studies can be performed. Here's an example of a study on a small village called Schutterwald. All data you can see here are open data. We were able to build a power grid, a gas grid, and estimate the energy demand for about 1,500 buildings. The network simulation was done with Pandapower and pandapipes. Here you can see the results of the power grid reinforcement if you add a lot of electrical heat pump systems. Finally, the costs for the energy consumers, but also the costs for the networks can be calculated. This can support investment decisions. So I hope this gave you a short overview of using Dave and pandapipes for hydrogen network simulation. If you have questions, please leave them in the comment section. Das war ein Video, präsentiert von Integrierte Energieinfrastrukturen. Schaut doch auch mal in die anderen Videos.